I started with and then I'm
对，稍微等等那个情况可以吃个。那大家喜欢吃巧克力可以吃这个，这是
哈萨克斯坦
巧克力，你要不要吃？然后回去尝尝，不要吃，分享一下这个。在线上反馈一下。
哎，姜老师能听到我们说话吗？
哎，刘老师可以的。
好，谢谢姜老师，谢谢您组织啊。
好
，OK, shall we go?
谢谢你，吴老师。
Okay. Thank you, Ms. Jiang. This afternoon, we have two distinguished scientists from Denmark Technology University, DTU, very famous institution, especially for renewable energy research, wind research. Professor Jakob Mann and Professor Mikkel Højholm. Hopefully, I best pronounced right. So, first talk will be given by Professor Jakob Mann. I have a very short introduction of the first talk. So, this forum is we call it Future Ocean Forum, right? It's from our academy called Future Ocean Academy, and myself also the supervisor of this academy. This kind of island or of multidisciplinary ocean research, oceanographers research. Also, today we'll have many online audience as well. So, Professor Mann, Jakob Mann is a professor at DTU and also the head of meteorology and remote sensing sections in the wind energy system division as a department of wind energy systems. He became professor of atmospheric turbulence and wind energy at DTU in 2003 and specialized in atmospheric flow with relevance for wind energy and remote sensing with Doppler lidars and head of meteorological and remote sensing section at DTU. Professor Jakob Mann was the president of the European Academy of Wind Energy 2014 to 2015. And I should mention that this year, Ocean University of China, OUC, is also a member, honorably become a member. Thank you for that. We also the previous president of EAWE's approve and recommendation. And now also Jakob is the founder of editor-in-chief of famous journal, peer-reviewed journal, Wind Energy Science. As Professor Mann is a facility scientist at the National Center for Atmospheric Research, USA. So today's topic is a wind energy research activity at the DTU. Yeah, very beautiful picture, I think so. Let's join me applause to welcome Professor Jakob Mann.
Thank you very much. It's a pleasure to be here, and thank you for the invitation to talk at this Future Ocean Technology workshop or series. Yeah, so this is one of our researchers standing by some decommissioned wind turbine blades from the world's first offshore wind farm in Denmark. So they were running there for 25 years, and now we use them to see what happened. In fact, they could last much longer. It turned out they were over-designed these blades. It was mine. Okay, so we are quite a big department of wind energy, and we are around 450 employees. We have more than 100 PhD students. We also have a education as a master in wind energy, where we, I don't know, not so many, maybe 100 to 200 people. We do not do a lot of teaching, but we have a lot of collaboration with businesses. So we have like 280 business partners in 42 different countries. We have research projects both with the companies, but maybe mainly with the EU Commission or the Danish funding agencies or private funding agencies. And we are partnering with many universities all over the world, and we are really welcoming guests. And we had the pleasure of having Xiaoying for 1.5 years, and also had Feng Gu for a month or whatever it was, a month and a half. So that we are really fond of that. We had some research facilities. I cannot go through all of them, but some of the most impressive ones is our Paul Lacroix wind tunnel, where we have a fan of 2.4 megawatts. It can reach more than 100 meters per second, and we use it for section test of wind turbine blades. And the special thing about this is that it's air acoustic, so we can listen to the blade, listen to how much noise it makes, which is of course very important for onshore turbines and less important for offshore turbines. So this is the fan, and this is the inside of the wind tunnel, where the walls can be changed to some Kevlar walls where the sound can propagate through. And we have a microphone array outside that can hear exactly from where on the blade the sound is produced. We also have many other facilities, and one of them was for a short while Chin's playground. It's a place where we test turbine blades, and not the biggest blades, only blades up to 45 meters. We have stands where you can bend the blades up and down all the time for a very long time. And now, I mean, we cannot use it for commercial blades really, because no commercial blades are this small, but we produce our own blades of either glass fiber or carbon fiber, and we can test those, and sometimes the tests go wrong, and we try to figure out what went wrong with these blades. But that's a part of the materials investigations. Then we have a research turbine. It's an old V52, so it's a Vestas 52-meter rotor diameter. On our campus, you can see our campus in the bottom here with nice fields, and it's in the countryside actually. And this is often equipped with a number of lidars, and there's all kind of measurements devices on the turbine. And we'll see more of that tomorrow when Jen will present her measurements of the blade defection with the automotive lidar. Then we have a test station for large turbine. It's mainly, let's say, it's a commercial activity from us. The wind turbine manufacturers, they rent a stand maybe for six months. They put up their turbine, and we provide the surrounding measurements, maybe sometimes also the measurements on the turbine, but typically we provide the measurements of upstream wind. Currently we have 9 test stands, and we can have turbines up to 330 meters height. In this part of the country, which is a very remote part of Denmark, this is the largest tourist attraction. So people can walk almost right up to the turbines and get a feel for how big they are, and that turns out to be quite popular. So currently, we have this summer put up a 21.5 megawatts Siemens Gamesa turbine. Has a hub height of 180 meters and it reaches up to 310 meters. Here you see this crane, the orange crane, is used to erect the big crane, which is used to erect the whole turbine. So it's really some big and impressive machinery. Here you also see the upstream mast measuring the wind speed at hub height, 2.5 rotor diameter upstream of the turbine, in order to validate the power production of the turbine for a given inflow wind speed. So it's called Østerild National Test Center, and we are currently expanding this test facility to the north. You can see the turbines here, but we are expanding it to this area where we have put up 4 of these systems, profiling lidars up to 1,000 meters to investigate the flow quality. We want it to be similar to offshore conditions, but this is some distance from offshore. So one thing we have to figure out is whether we have to cut some of the forest that is here in order to make the wind profiles more like offshore wind profiles. We also have pairs of lidars, one at the position or potential position of the wind turbine and one at the potential position of the upstream mast. But since we're looking at 450 meter tall wind turbines, the rotor diameter might be 400 meters. So the upstream distance where you have to measure the wind is a kilometer. So quite some distance. Yeah. So we have gotten support from the parliament in Denmark, and it's an investment of about 1 billion yuan. Good. So we hope people will still use the test station. We also have many other facilities. One quite new one is this kind of a shower where we put pieces of a wind turbine blade and rotate it very fast through the rain. That's because what's called leading edge erosion of wind turbine blades is becoming more and more important. So we have so when the blade hits the rain, then it erodes the material, and in order to study the material properties and so on, we need a test facility like this. Okay, we also have what we call a facility, which is lidars that are coordinated in motion, and Michael Sjöholm will talk much more about that. But the basic idea is that we have 3 lidars so that we can get the 3 components of the wind vector, and they meet at one point, and then this point can move around and investigate a flow, either flow in a wake or flow behind a building or whatever. And we have 2 types of systems. One is based on continuous wave lidars. They have a maximum feasible range of a couple of 100 meters, but they can also go very close. And they can have very fine resolution and measure very quickly, like several hundred hertz of wind measurements. And then you have another system which is pulsed lidars that can measure up to much longer distances, hours, typically 7 kilometers or so. But the main point is that they are coordinated, that you can control from one computer and assemble the data there. So one example of the use of these, in this case, the short-range wind scanner is here, where we investigate the wake behind a tree. So for us, atmospheric flow is very important, and trees are the objects that take up most momentum from the atmosphere. So it's important to understand what is the dynamics, how much momentum does the tree take up. And for that, we made an experiment where we have an inflow mast, and we have these three lidars, R2D1, R2D2, and R2D3, to measure the flow in a plane behind the tree. And this is what we get. Here's the tree. Here's the inflow, which is homogeneous. And in the outflow, we see a wake deficit. Actually, the winds in the wake is maybe only 20% of the free wind. And this way we can measure how much momentum the tree takes out of the atmosphere, integrating the deficit behind the tree. We also have strain gauges on the tree, so we can measure direct the force on the tree. That's one example, but of course, many other examples of wakes after turbines, and Mikael will show many of these. This is again the tree. We can see this deficit behind the tree. We normalize with the upstream turbine, and you can see that we get down to maybe 20% of the upstream wind. But we can also use this system to measure turbulence. If you go down here, you see the fluctuations in the wind direction, and we see that fluctuations cluster around the edge of the wake, where you see enhanced turbulence. See, that's also where the shear, the gradient in the wind, there's two gradients here, the vertical gradient, the horizontal gradient. That's where the gradients are largest. Finally, we can look at transport of momentum from the free flow into the wake. Here's wake momentum transported from the left to the right, and here's from the right to the left. So there's a convergence of momentum into the wake, so it gets depleted. Here's the vertical direction. We can see there's momentum going in from above. That's because these short-range wind scanners, they measure a quite small volume and they measure pretty fast. So in this way, we can also get this statistics, turbulence statistics, to understand the wake dynamics. So on. Good. I mainly work with meteorology and remote sensing. It's in a big experiment we made in Portugal some years ago with two parallel ridges, which I'll come back to. You see one ridge here. I'm standing on the other ridge, and it was a hot summer with temperatures up to 42 degrees. So we had cooling system here, but we had to put some reflecting, insulating things around the lidar in order not to overheat. That was really a problem at that time. And you can see some of the meteorological masts we had in the experiment. Good. But in general, what we do is to investigate all things that has to do with meteorology that are also important for wind energy. So that's, of course, wind speed, turbulence, but also precipitation, rain or hail, or lightning, or many things that has to do are important for wind energy. So lightning, of course, can destroy blades, and hail can erode the blades. Winds are the resource for the energy, and turbulence can harm the turbine. So now I'll come with examples of our work, and the first example is this offshore floating wind farm, where Equinor, the Norwegian energy company, they have 5 floating turbines. They are spar buoys. I think the spar buoys, they go out down to like 100 meters. They're really deep ones, so they don't move very much actually. But they have 5 of these turbines in the world's first floating offshore wind farm. They're 154-meter rotor diameter, and they are placed west of Scotland, roughly 40 kilometers from the coast, in this pattern. And 2 of these turbines have had the lidars mounted on them. So this is a top view where you see one turbine with a forward-looking wind iris lidar from Vaisala, and a backward-looking scanning lidar from Galleon or Halo or now Lumibird. And this lidar can go out to almost 2 kilometers, and the next turbine is 1.5 kilometers away. So we can follow the wake all the way to the next turbine. You can see a little bit of the wake of the next turbine. This is a side view, so the scanning lidar measured at a constant height, while the forward-looking lidar looks horizontal with one beam and slightly tilted upward with the other two beams. And you can see much more in wind energy science at this UI. So what are we using these measurements for? So first of all, I'll talk about the inflow. So the inflow, we use all the lidar measurements at all the distances measured out to, I think it was 400 meters in front of the turbine, and we have to have a model in order to extract parameters from the measurements. So we make a model of the wind flow, and then we fit that to the line of sight, where we have projected this model onto the beams and measured at various distances at various heights z. So in the first component, the long wind, the component perpendicular to the rotor, you would say the horizontal component perpendicular to the rotor, is made up by the velocity at infinity plus a term which has to do with the shear, which we assume is linear. C is the height away from the rotor center, so we have a linear shear. Wind speed might change with height. And then we have an induction factor, which is a function of upstream distance only, we assume. And it's 1 minus the induction factor plus a function which decays to 0 as x goes to infinity or minus infinity. R is a rotor radius, and XL is the position of the lidar behind the rotor, which is only 4 meters. So that's the second term is the transverse component, which is the transverse component of the free flow, plus how the wind changes direction with height, basically. So the veer, and then we assume that the last component is 0, at least on the mean. So this is how we fit to this lidar data. We have the 4 beams looking forward, 2 are horizontal, the blue and the green. And you can see how, as a distance from in front of the rotor, that the wind speed decreases as you approach the rotor due to the induction. The 2 measurements are not the same, and that's because we have a transfer component, so the wind is coming more into beam number 4 than beam number 3. There's an angle, yaw angle misalignment. And the other 2 beams, the ones looking a little bit upward, they also see the induction close to the rotor. Then they kind of decrease with distance. And that is, according to the model, because the wind speed decreases with height. There's negative shear in this case. So from all these things, we can also look at the veer. We can fit the veer, and we can get the induction factor. So how much the wind is decreasing as we approach the rotor. These are the tilt and the yaw of the whole turbine, and this is just a number indicating the error on the fit. So the inflow conditions, we look at the shear, which grows with mean wind speed, but you can also see quite often there's negative shear. So we have quite big values of negative shear sometimes, and that's often when the fit is not so good. So maybe the wind profile is not linear over the rotor. You can also see on the veer, so how much the wind changes with height, that generally is the veer is negative quite consistently with some scatter. and that's because of the Coriolis force. So you have the wind turning with height in a certain way on the northern hemisphere. We can also look at the induction factor as a function of wind speed. So that is supposed to be a constant at low wind speed and then drop when you reach rated and decrease then with wind speed. And that is basically what we see. The backward-looking LiDAR, it can look down to the next turbine almost. I think that's the next turbine we see there. And what you have in the top plot is low turbulence intensity situation. So here there's only 2% turbulence intensity according to the LiDAR. Maybe there's in reality a little bit more. And there's also 2% here. This is below rated 10 meters per second. This is above rated 14 meters per second. And we see quite some difference. We haven't really figured out why the wake is kind of flattening out like this. Maybe there's a lot of veer that makes that. The veer is 0.03 per second. So maybe it's a veer that makes the wake behave this way. Down here, it's higher turbulence. So this would probably be a stable atmosphere in the top. And here it's more neutral to unstable. And here we again see the wake propagating downstream, maybe more defined in this case. We didn't see any indication of the movement of the turbine. The floating turbines is moving, but these turbines are not moving very much. But there has been some suggestion in the literature that if the turbine is moving quite some, then it might dissolve the wake more quickly. But we didn't see that. This indication. Finally, we can use this experiment for looking at turbulence. So turbulence is typically described by the spectrum. So the variance of the different components divided up on frequency. We have the longitudinal component U, the transverse V, and the vertical W. We also have the negative cross spectrum between U and W due to the momentum flux down into the ground. And this is an onshore spectrum. It's quite a lot of 1 hour sonic measurements from another test station we have in Denmark, at 80 meters above the ground from some homogeneous direction. And what we see is this very nice shape, which is also reflected in the IEC standard, the International Electrotechnical Commission standard on how to design a wind turbine and what loads to see. So that's fine. You can maybe see at low frequencies, maybe something is happening here with the V spectrum, it grows. But if we look at an offshore spectrum, they can look quite different. So this is again spectra from a mast, 81 meters above the sea level, the FINA 1 platform, and it's one hour time series that has been used. You can see the kind of the nice shape up here, but then at low frequencies you see something else happening, and we call it mesoscale fluctuations. It's probably weather kinds of fluctuations that are not a part of the standard typically, neither of the two spectral models in the standard. We also call it 2D turbulence because we don't see anything in the vertical component, at least not at this height, 81 meters, but the two horizontal component, U and V, they have a lot of energy at these low frequencies. So therefore we made a model for low frequency anisotropic wind fluctuations and coherences in the marine atmosphere. And here you see a typical spectra. So the measurements is measured by the LiDAR you just saw from the High Wind Scotland. and then you can see if you try to fit a normal three-dimensional turbulence spectrum to to the data, then we miss something at low frequencies. So we have added this two-dimensional fluctuations, and then we can, of course, with more parameters, fit the rest. And yeah, we tested it with this forward-looking LiDAR system from this floating turbine. This is another example with more low-frequency variations. Yeah. So what do we do? So we have the normal turbulence in the standard, which is my old model, the MAN model. But then we add also a term which has to do with this two-dimensional low-frequency turbulence. So you see that here two beams, the two lower beams from before, and we see how it can fit the whole shape. So this is a standard model, and then we add something that has to do with the horizontal wave number, and we have a real two-dimensional model of that. The MAN model has these three parameters, L and alpha epsilon, the multiplier, the inertial subrings, and this is the length scale. And we assume an anisotropy parameter. We can then fit these two parameters, and we can also fit the multiplier for the low frequency range. Then we can kind of fit the model based on these spectra. But what we then can do is to predict what is the coherence between the two beams. The coherence of the two beams is important for, for example, for wind load. No, so LiDAR-assisted wind turbine control, how correlated are the winds at this distance, or wind loads. More correlation gives more of some loads and less of other loads. So we can, from the model, predict what is the coherence for lateral separation of the U component. And so we fit the model and get the parameters. Then we can also measure the coherence from the two beams. What is the coherence between the two beams for lateral distances from 26 meters up to 206 meters? And then we can predict the coherence. And if we ignore the two-dimensional fluctuations, then we get these coherences, and we think that the new model is slightly better to model the coherences. Anyway, we can then use this model to simulate large-scale fields. So these boxes of turbulence in the two horizontal directions are quite large, like 15 kilometers times 60 kilometers. So it's quite large fields that can be used to study those, but also meandering in wind farms. So here you see two examples. So this is just normal three-dimensional turbulence from the standard. You can see the wakes. They meander a little bit, but they kind of keep the direction. While if you include this low frequency variations, then you can see that the wakes start to meander quite a lot more. And in this simulation, and that actually changes some loads, because if you are a downstream turbine here and you have the wake coming in over the rotor and out of the rotor, then you have some new dynamic loads on the wind turbines. So it might be important in the wind farm calculations of loads. But we are trying to investigate the turbulence in more detail. So, for example, we are doing this experiment on the west coast of Denmark, funded by EU. Here we have three scanning lidars, a new Weissela, a new lonely bird, and a very old Weissela Leosphere. And they look over the ocean. From this church you saw in the background, there's a church. So they look over the ocean in this direction. Then we have another position where two lidars looking down, and they meet then in 6 points where we can measure the horizontal wind vector. Then we can correlate all the horizontal wind vectors in different points and for different distances, and therefore understand more about the structure of atmospheric marine turbulence. Yeah, so these are the crossings, just like from, I think it's like from 50 meters separation up to 200 meters separation, so representing the diameters of large turbines. This is measured both at 150 meters, and we tilted the whole system, so they also measured at 250 meters. One very subtle thing with this is pointing accuracy. I mean, the pointing accuracy of the LiDAR might be nominally something, but then if somebody pushes to the LiDAR or something happens, then you're not sure any longer. So we had to do some special things. We have this drone with differential GPS, so we can look at the position with a centimeter accuracy. And it was flown out to some 100 meters, and then we could find the drone with the LiDARs and be sure about where we are pointing at. This is also at our campus at Risø. So, then we have validated this new model with called Jakob Mann model with the offshore turbulence. We can also investigate low-level jet climatology with these data, and all the data are available online now, so they can just be downloaded by everyone. This is the next speaker, Mikael, and our current PhD student, Ansh Patel, who has been analyzing this data quite a lot. So, and this is the west coast of Denmark, with the church in the background. And these turbines out here in the horizon is our old test center. We have also worked on dual Doppler measurements like the ones offshore you just saw, but over land. And that is coming back to the picture where I stand on two ridges in Portugal. So this is collaboration between Portugal and Denmark on measuring turbulence and mean wind speed with dual LiDAR instruments. So here are the two ridges, and we were operating eight or nine, I think it was 9 LiDARs, scanning LiDARs in this experiment, but in total there were 21 scanning LiDARs and a handful of profiling LiDARs, a lot of other instruments, balloons, nanometers, and 51 meteorological masts with sonic anemometers and other instruments. And the purpose here is to look at virtual masts. So we have some virtual masts, 1 and 2, 3 and 4, and they consist of a real mast, and on top of that we have a virtual mast consisting of 2 LiDARs meeting above it and scanning up and down, and the same with this 100-meter mast in the middle, LiDAR scanning up and down above that with some overlap. The results from this campaign, now we just look at a virtual mast of 1 and 2. And this is 1 and 2, the horizontal wind speeds measured by the virtual mast compared with the top sonic anemometer at 100 meters is very nice. I mean, they measure basically the same with not too much scatter. But when it comes to turbulence, the situation is slightly worse. First of all, there's more scatter. That's one thing. But also for some configurations, the slope is not close to 1. It's slightly underestimated. And depends on the geometry, how big is the angle between the LiDARs, and then also the fact that the LiDARs average over some distance, around 30 meters. So it loses out edges that are smaller than 30 meters. And this particular problem with the losing out some turbines because of the measurement volume is the next thing we are working on. This is a preprint under consideration for publication in atmospheric measurement techniques. And here we try to calculate the average Doppler spectrum over 10 minutes of the LiDAR. And then we fit that to a mathematical model, which is based on the physics and mathematics on how light scattering comes to a spectrum in the machinery. So we have done an experiment at our campus at research, where we have a turbine here, the V52 you saw before. We have a mast, and then we have a small telescope here and looking at one of the sonic anemometers on this mast. So here you see the telescope for a pulsed LiDAR. And here you see that, I mean, we have calibrated the rifle sight here, so we know that okay, we are very close to the sonic anemometer on the mast. So we can compare the line of sight measurements from the LiDAR with the 3D velocity measured by the sonic anemometer projected onto the beam direction. They should be the same. And if we look at the 10-minute mean velocities for medium pulses, so that's a measurement volume of 50 meters, then it's quite boring to look at the sonic and this spectral model that we fit to data. They give the same, and it doesn't matter whatever we do with the data, we always get the same mean wind speed, which is nice. But if you look at the turbines, then the things gets a little bit more uncertain. Sometimes when the turbulence is very low, turbulence standardization very low, then the LiDAR kind of, or the model we fit to the average Doppler spectrum underestimates the standard deviation. It gets worse when you look at the 200 nanometer pulse, so a measurement volume of 30 meters or something. Here there's much more scatter. And if we make a scatter plot, one versus each other, then we see the wind speed is quite boring. It reproduces well the sonic measurements. But the turbulence, well, there's more scatter, but still the slope is very good for the 400 nanosecond pulse. But if you look at the 200 nanosecond pulse, the mean wind is still fine, good enough. But you see there's too much scatter on the turbulence measurements, and sometimes we get zero turbulence, what's the turbulence standard deviation from the LiDAR. So we need to work a bit on that. But it's a first step to avoid this impact of the measurement volume. Good. Last, very shortly, Chin will also talk about this tomorrow. We also used had a drone where we measured the flow below the drone. This is CFD measurements of the velocities below the drone, and these are the measurements. Chin will explain more about that tomorrow, I think. We've also tried to use Doppler LiDARs for rain measurements, which was something that Xiao Yang was doing some years ago. Okay, so that's all for now. Thank you very much for your attention. Maybe have time for questions.
Yeah, thank you. That's very informative talks. And we do have a question from online. I think I heard from Ms. Jiang. And it's open time for questions. So please raise your question or just type in the chat box or leave the message on the different platform. We're online now. And Secretary of Academy, Ms. Jiang, will forward your questions. So Oh, there's one question. Okay, I can repeat. Maybe I can also type the question. Okay, I can repeat. When blending, I think merge the matte mask scanning LiDAR and UV-based hot film probes across at 2 kilometers range with 150-meter elevation change. How do you systematically weight each data stream in a common or in several common frameworks to avoid overweighting high resolution but potentially biased sensors? And what cross validation benchmark like triple co-location or virtual mask measurement prove that the field actually improves safety low boundary conditions? Well, it's a complicated question.
Yeah, very specific and complicated question. So UAV-based hot film probes. Wow, that sounds like a very complicated way to measure wind and prone to some biases. Maybe I think mid-mast and scanning LiDAR, they are by far the most robust ways, and I think they should be trusted most. So,
okay. Here comes the second one. The second question. Current LiDAR and radar system are still limited by either spatial resolution, averaging, and temporalizing. Okay. When resolving sub-second, sub-meter edit in the rotor plate. So, what specific hardware or algorithm breakthroughs do you see as essential to push the resolution, let's say, less than 1 meter or higher than high 10 Hz domain without introducing phase noise? And how do you quantify the resulting uncertainty reduction in potential load estimates?
That's also a complicated question. I think the method we propose here has potential. So instead of using a time series of wind speed from the LiDAR, we take the 10-minute average Doppler spectrum of this pulse LiDAR, and that should eliminate the problem with spatial resolution in the way that you will get the right standard deviation. You don't get the full spectrum or anything, but I think that has potential. So that's basically not improvement in hardware, but it's improvement in data analysis. Then going down to 1 Hertz. Oh,
yeah, 10
Hertz. I mean, we can do that with the continuous wave LiDAR. We have done field measurements with 400 Hertz.
400 Hertz.
Yeah, 400 Hertz where we scan rapidly up and down. And that was after a cliff where we can make a wind profile, 7 meters tall wind profile in a tenth of a second with roughly 40 measurements. So we can do that very quickly with a continuous wave LiDAR. A continuous wave LiDAR still has averaging volume depending on how far you focus, but that can also be eliminated by looking at the average spectrum of a continuous wave LiDAR. The average spectrum for a continuous wave LiDAR is LiDAR, and the company ZX LiDAR in the UK, they use that technique for the nacelle mounted LiDAR to get turbulence without impact of measurement volume. So that can be done.
Yeah. Two questions. So far, we have 2 questions online. So maybe audience at this meeting room.
One way.
Yeah.
It's about the turbulence estimation you get on the page 43. It has this time series.
Yeah. 43 somehow. Yeah.
Yeah, I noticed that like where the model underestimates turbulence, the model usually give 0, right?
Yes. The reason, I think, one of the reasons, 2 potential things. One is that we don't account for change of the mean wind speed along the lidar. If there's no turbulence, but the mean wind changes along the lidar beam, then you still would have some width. We don't take that into account. That's one thing. Other thing is that the model we get assumes that the pulse is Gaussian, and we have measured the pulse shape very accurately. And it turns out that for the shorter pulses, it's quite skewed compared to a Gaussian, and that might also impact it. But we haven't done the math to figure out exactly how to do that. But so there's two things: the pulse shape assumption is not right, or the mean wind speed along the lidar beam is not constant.
Thank you for it. Yes, please.
Go to the slide where you show the impact of two-dimensional effect on the waking energy.
Can you
go back to, or just click here, yeah. Then I can control it.
Yeah.
This one.
So and the question, maybe I missed it. So in the first plot, the inflow is only the three-dimensional man turbulence.
Yeah.
With the IEC parameter or
No, I'm not so sure. Probably maybe reduce turbulence intensity, but I think it's a standard IEC length scale and gamma, but turbulence intensity adjusted to offshore conditions.
those simulations are performed top to bar.
Yes, what we now call dynamics.
You investigate the turbine loads of those
Yeah,
turbines.
yes. And
Did you take some?
some loads are actually increased in this case.
Yeah. Okay.
So, but I can't really remember exactly what loads, but it does have a difference, 10-20% on some loads.
Yes, may I have a question as well? So, I think we've seen as a page 23. How can we do that?
You just or maybe if you move the cursor to the this one. Yeah, click here.
Okay. Yes, I think for this plot, because you mentioned that there's a rolling angle due to the torque, so the pair of the two beams will change the elevation angle actually.
Yes.
And actually, when we do the lidar system control, that's during the rated power phase, right? And so maybe the rotating angle is a fixed. In your case, it's 7.2, right? 7.2 degrees.
The turbine leaning back.
Turbine leaning back. Is this leaning back or rotation? No, that's the Y.
The Y is rotation about our Y-axis, which is perpendicular to the wind direction.
So this is rolling. Yeah.
Yes, so rolling back. So that's because the wind is pushing the rotor. This is because of the torque on the rotor when it's put to the side.
Okay, go to size 1.2.
Yeah.
Okay.
So
you have to calibrate it, or maybe how do you know this 1.2? You have a measurement.
IMU system.
Yeah. Okay.
At that you can see it.
IMU system. So so do you recommend that lidar system should have this incline angle measurement as well, or?
Yeah, and actually the wind Iris has that.
Yes.
But the quality of the IMU was not good enough.
Okay.
So he used the one that was on the nacelle.
So this rolling angle actually somehow is fixed, right? It's not a swing or not.
It depends. Yeah, it's. I mean, it varies a little bit.
Well, a little bit.
Much, and it also depends on wind speed. Yeah. Also torque and so on.
Yeah, I see. But still large difference, even with 1.2 degree.
Yeah, like these are very different.
Yeah.
That's because, I mean, these horizontal ones are different because we have a transverse component relative to the rotor. So wind comes more into this beam than that beam. Then if we go higher up, this V component will actually be more negative. So we then get even larger difference. So it's wind comes from it's difficult.
I understand.
And then higher up it's different.
So the blue and the green one is horizontal.
That's the horizontal ones. Yeah, those two. And the orange and the red are the one.
Can I ask, is it due to the lack of the amount of data? That's why the red dots doesn't fit so well as compared to the.
But I don't think it's lack of data. I think it's the model assumptions are quite crude that the C and the B are exactly linear, and so it's
Yeah, but it only happens to the being outlined. Like the red one. It's that less perfect than it of other.
I think it varies from situation to situation. In this case, its error is 1 meters per second. So that's the average distance here. In other cases, it's smaller. Other cases, it's larger, up to 0.5 sometimes.
It still is a quite good feature.
Yeah. So it's useful.
Thoughts, discussion. Anyone else? Yeah, Pauline, please.
I have questions about around the boundary later. You may later have some eliminations in the complex theory. But we have found that the different type of theory give a different factor in later. So it is necessary for us to apply a correction such as FD to ensure later accuracy.
Yeah. You are absolutely correct that in complex terrain, typically on the hilltop, the flow goes around and you could get too low wind speed because of the propagation. But I wish I had brought some other slides which show flow in complex terrain over one of these ridges in Portugal. And sometimes the flow follows the terrain and is stably stratified, but other times the flow kind of continues up, and then because you're recirculating, actually it's unstably stratified. So the correction also depends on stability. So you have to use CFD with stability, and it really gets complicated. So it's a big challenge, complex terrain. Because maybe you just use a tri-static or bi-static system, dual Doppler gliders. We also did that in Portugal, where you had a dual Doppler system scanning the flow over the ridge up high. Dual Doppler gliders, which have some good communication in the complex terrain. Conical scanning or something like that. It's problematic.
You have the dual Doppler to set them to PPI mode or just for 2 modes?
Oh, in this Portuguese experience, we knew the terrain, so we just did the line to spin 80 meters above the terrain, so follow the terrain 80 meters above the ridge top. So that's how we use Doppler line.
I found that you use your scanning laser and turbulence is better than ground-based ground laser. Do you have any suggestion for us about laser's turbulence fraction?
Is this a big subject? But dual Doppler lidars is pretty good. Yeah, there's still some errors, but it's better than ground-based molecular scanning lidars. I still think this spectrum on the top slide, I should give some way to correct and figure out what are you missing. We're working a lot on it. We're also working in postdoc that works on it's not the energy dissipation from the line loss and so on. It's a big and interesting topic, but I think we solve it.
Yeah, we about turbulence, we have we have done a lot of work to research it, but we also still a lot of bad questions.
Yeah.
Yeah.
We can discuss more.
Yeah. Thank you for all the questions. Since we are running out of time, so we can shift to the second one. The audience here